I'm going to continue. I'm going to do two examples. Okay, one from yesterday, complete the one from yesterday. Okay, so just to recap quickly, the steel column support to eccentric load is assumed to be pinned at its top, fixed at the bottom, and is fully braced against buckling about the y axis. Two things we have to determine: the maximum deflection, the column, and the maximum stress in the column. We are given that the Young's modulus of the steel is 200 gigapascal and the yield is 360 megapascal. So we know that there will be buckling about the x-axis. Okay, so P, we have determined P yesterday. Okay, so what's so unique about this problem over here is there are two loads and two different eccentric values. Okay, so we have to get it to be a single value, and what's the equivalent value? So we have to find P, we're going to find E. So P, we discovered that is 180 times 10 to the power of 3. E, we found that 64.444 times 10 to the power minus 3. So now we know both P, and then the next thing we have to determine is our PCR, which we did yesterday before we end. Okay, before we determine our PCR, we have to this is the critical load formula. Okay, and then I show you two methods of determining the second moment of area. After we have determined the second moment of area, we have our PCR. So just quickly recap, we know that we have to calculate the maximum stress is equal to P over A1 plus by EC over R squared. And then we have our secant. And then we have our pi over 2 square root P over PCR. Okay, so we have our P's. Okay, we have PCR. We have our E. We don't know our area yet. So if we were to take this diagram, take this diagram, with reference to the diagram. So our area will be equal to twice. Okay, so width is, so I'm going to take my width as 100. Okay, my depth is 10, and then plus by 100 times 10, or 10 times 100. Okay, so this will give us an area of 2 times 100 times 10 plus 10 times 100 is equal to 3000, or 3 times 10 to the power 3 millimeter squared. And if we change to meters, it's 3 times 10 to the power minus 3 meter squared. Okay, so we have these sets of information. So now we have our area. The next thing we have to determine is our R squared. So we know that I is equal to AR squared. So therefore R squared is equal to I over A. We know our I value. Our I value is 6.9 times 10 to the power minus 6. Give out our cross-sectional area, which is 3 times 10 to the power minus 3. So this will be equal to 6.9 minus 6 divided by 3 power minus 3 is equal to 2.3 times 10 to the power of minus 3. Hold on. Yeah, it's 2.3. 6.9 power minus 6 divided by 3 power minus 3 is 2.3 times 10 to the power minus 3. So we have our R squared. The next thing we have to determine C. Now, what we are the C value? Okay, so we are looking at the centroid or the axis is IXX. Okay, so we have determined our IXX. So the axis of interest is our XX axis, which I draw in green. Okay, so the C value is the maximum distance. Okay, so that is the C value. So this stage, it is if you take C in this direction or C in the opposite direction, does not matter. Okay, because the magnitude are the same. But if you look at how the structure will deform, so if I'm going to copy this whole thing, come on, hopefully it works. So if you see, sorry about that. Let's see, let's try again. It's going to take the whole thing. Come on. Okay, let me just take this image and do the reanalysis. Okay, right. So this is our structure now, right? And we know that this is our Y. And then we know that this is our Z. And then we know that we have a rotation about X. Okay. So we have calculated the moment to be acting somewhere over here. The resultant moment. Okay. So this is our 180 times 10 to the power 3. And then we realize that there's a distance, the E distance, which we found yesterday. And I think the E distance is equal to, did we have it over here? 64.444. Okay, so it's 64.444. Okay, so we realize that the moment vector will go this way, right? So this will be compression. Down here will be tensile. So how the structure will deform is the structure will deform this way. Okay, we know that for a fact. So the correct value to use, okay, we have to use the compression side. So this is under compression, and this is under tensile. Okay, by right, we have to use this C value over here. Okay, but for this case, it does not matter because the left and the right is the same. The next example that we're going to do is going to be different. Okay, so we're going to take the value to be equal to, so this is 50, right? So this is 10, so it's 60 millimeters. So now we have determined our C is equal to 0.06 meters. Okay, so now we have every information. We are good to calculate our maximum stress. Okay, so now we can calculate our stress max. So the P we had is 180 times 10 to the power 3. Okay, divide by our cross-sectional area, which is 10 times 10 to the power minus 3. And then we can we have our bracket 1 plus by our E, we know is equal to 64.444. And then we have our C, 0.06. And our R squared is 2.3 times 10 to the power minus 3. And then we have our secant. And then we have our pi over 2 square root, then P. And then we calculate our PCR, which is equal to 772.112. 772.112. So 772. Okay. So we have everything available. So like what I said, you put them, you calculate some values first, okay? Because I will give you part mark. If you calculate everything and your final answer is wrong, I cannot give you part mark. So when I grade, okay, 3 power minus 3, So this is equal to 60 times 10 to the power 6, right? And then we have 1 plus by 64.4444 power minus 3 times by 0.06 power 2.3 power minus 3. So it is equal to 1.681. So I'm having a square bracket. Let me compute everything, then I'll show you the grading scheme in the term. That's how it works, okay? So you have 1 divided by cosine bracket pi divided by 2 times by square root 1 bracket 180 power 3 divided by 772.112 power 3 close bracket. Then make sure I have all my brackets. I need another bracket. Okay, and that is I get 1.37776. Okay, so in our marking scheme, right, if you calculate this value, you get half a mark. Okay, you get 0.5. This is worth 0.5, and this is worth 0.5. Are we clear? Okay, so these are the part mark is given, and then we have our final answer is 60 power. So it's equal to 1.681 times 1.3776 plus by 1 times by 60 power 6 is equal to 198.945. Okay, so 198.945 times 10 to the power 6 Pascal. Okay, now, so in the marking scheme, what will happen is if you do this, you get 0.5, 0.5, 0.5. Okay, so you get 1.5 marks. If you don't have, let's say, if you don't have this, okay, you did not do this, you just give me the final answer, then you get 1.5. Okay. However, if this answer over here is wrong, it's as good as 0. Okay, if you don't show me your partial values. Are we clear? Okay, so don't lump everything together. It's quite dangerous and it's difficult for you to check. I hope you understand. Okay, so we have calculated that this is equal to 198.945. So given in the question, so if we look at the question, the yield is 360. So we can write down here that the stress max, okay, is less than 360 times 10 to the power 6 Pascal. So structure, okay, you can write structure will not buckle under or buckle due to eccentric loads or loading. Okay. The next part of the question is we have to determine the Ymax value. And I'm going to show you, you can use two formulas or two different formulas. The outcome of the answer is the same. So the first formula that we're going to use is we're going to use Ymax, the one that I highly recommend you all to use. So Ymax is equal to E, right? Then we have secant, and then we have pi over 2. Then we have square root P over PCR. Now all this looks really, really familiar.